right, thank you all for waiting. So I guess we can start with this 13th webinar in the EU Africa R&D facility webinar series. Maybe first some housekeeping. I will be presenting for about 1 hour on the topic of parcel-based crop monitoring from space. During my presentation, you can put as many questions as you'd like in the Q&A section, which should be accessible to all of you. And then after the 1 hour presentation, we'll take half an hour to and try to answer most of your questions. So let's get started. Maybe first a brief introduction about myself. So my name is Jeroen Degeriks. I work at Vito Remote Sensing, which is a research institute located in Belgium. We, in our remote sensing unit, we are dealing with all aspects of Earth observation, going from satellite development, sensor development, all the way up to applications. And I myself am part of the agricultural applications team at Vito Remote Sensing. So my job is actually to collect Earth observation data and turn that into valuable information products for all stakeholders in the agricultural sector, going from the individual farmer all the way up to agricultural ministries and international agricultural organizations. And in this presentation, I will be showing you parts of my work and the work of my colleagues as well. So what's on the menu for today? So I will briefly talk about why we are engaging in parcel-based crop monitoring using satellite data. What do you need for that? General concepts, also briefly touching upon pixel-based approaches versus parcel-based approaches. Then I will have quite a large section on the different applications that we are currently active in, or the different monitoring potential applications based on satellite data. And then I'll conclude with some practical guidelines on how to get started yourself with the data and introduce you to some tools. So let's get started. First of all, why we need this parcel-based crop monitoring in the first place. As you know, world population is growing tremendously, and we all need to produce more food on the same amount of land. So that means that we need to carefully think about our global food production and make sure that it is running more efficiently. And that is one thing we can do to ensure production efficiency is to carefully monitor what is happening on our individual agricultural parcels. So that is really the topic of today. So here we want to zoom in on our parcels to get information on how the crop is doing, what crop is growing, where, and this information is extremely valuable to safeguard global food security. So like I said, questions like what is growing where, how well is a certain crop developing in a certain region, what are the impacts of extreme weather events on local crop production in a certain region, what are the expected yields, etc. What is the impact of certain agricultural management choices, for instance, irrigation schemes, how efficiently are they? All those questions can be answered if we carefully monitor our parcels. For the individual farmer, there's an interest as well, of course, because based on this near real-time information that he gets for his crop on his fields, he is able to make better decisions in terms of crop management. So where to irrigate, for instance, when to apply fertilizers, etc. So this is the overall goal of the term precision agriculture. So based on real-time information, a farmer can make better decisions and boost his productivity. So what do we need in order to monitor crop production at the parcel level? I want to start obviously by the satellite data itself. So Sentinel-2 satellite, Sentinel-2 data is available from 2018 onwards, and that has really been a major game changer in our ability to monitor crops at the individual parcel level. So both in terms of the spectral resolution and the spatial resolution, it's a tremendous improvement compared to the Landsat satellites that were previously available. So Landsat was at 30-meter resolution and a limited amount of spectral bands, so limited amount of information, whereas Sentinel-2 is at 10 to 20-meter resolution, so really at the parcel scale. And I know it sounds a bit small, the difference, but it really makes a tremendous difference going from 30 to 10-meter resolution. And also, Sentinel-2 comes with these additional red edge bands, which are pretty important when it comes to monitoring of the condition of your crops. Also, in terms of revisit frequency, so how often do we get an observation from our satellites? The Sentinel-2 is really stepping up the game compared to Landsat. Here in this image, you can see that on average, we get an image from Sentinel-2 every 5 days in most regions across the world. Whereas for Landsat, that was rather every 16 days. And of course, if a farmer needs to make management decisions based on real-time information on his parcels, then you want this information to be updated very regularly. But even though with Sentinel-2 at 10-meter resolution, parcel-based monitoring is not feasible everywhere. If you look at the US or Europe, where you typically have these very large homogeneous parcels, the resolution of 10 meter will obviously do. But if you move to for instance, African country or tropical regions in Asia as well and Southern America, where you have lots of smallholder farmers having mixed cropping, where multiple crops are intermixed on an individual field and the fields are very small in size, then even that 10-meter resolution probably won't suffice for your application. As an alternative, there are some commercial data providers offering even higher resolution data, and I think Planet is one of the most famous ones. But there are others as well. So Planet offers, or at least tries to offer one image of the entire planet. So no matter where you are on the planet, you'll always have one image every day at around 3 meter spatial resolution for, again, also a limited number of bands. I won't go into too much detail on the use of Planet data in this webinar. I want to focus here mostly on freely available and open satellite data. But if you want to learn more, here's a link or a QR code you can scan to find out more about agricultural applications specifically based on Planet data. Talking about the free and open source satellite data, there are some advancements in the use of deep learning algorithms to tackle this problem of the 10-meter resolution for Sentinel-2. I again won't go in too much detail here, but just note that the lack of spatial resolution for Sentinel-2 can partly be compensated by using advanced image analysis techniques. So in this example, researchers have actually achieved to generate a cropland mask, so the distinction between cropland in red and non-cropland in gray, at 2.5-meter resolution, purely based on 10-meter resolution Sentinel data. So while it is, of course, very challenging, there are possibilities to artificially increase the resolution of your data. When it comes to using satellite data, one other important sensor I want to highlight here is Sentinel-1. Sentinel-1 delivers radar data, so it's quite different from the Sentinel-2 sensor. So radar, it's mainly an active remote sensing technique, so that means that the sensor emits radiation and captures that radiation, which is reflected by the Earth's surface. The big advantage of radio waves is that they can penetrate through clouds. So often in tropical regions, we have limited data availability from Sentinel-2 because yeah, it's an optical sensor, so it cannot see through the clouds, but radar data can. So in that sense, it's already nicely complementing the Sentinel-2 data. And in addition, the radar signal holds information on vegetation structure mostly and moisture content. So again, that's a nice complementation to the data offered by Sentinel-2. It's available at 20-meter resolution and normally every 3 days. Up till recently, there were actually 2 Sentinel-1 satellites in orbit. One, however, failed. So in some regions across the world, currently the availability of Sentinel-1 is rather limited. But I will also share these slides with all registered participants after this presentation, and you will find some additional links to more information about that if you're interested. Okay, so we have all this freely available satellite data, but we are really facing these huge storage requirements. Just to give you an idea, Planet, which I mentioned earlier, that sensor or that constellation of sensors captures 25 terabytes of imagery every single day. For Sentinel-1, it's 10 terabytes. For Sentinel-2, it's also a few terabytes. So as opposed to the low resolution monitoring activities that you might be familiar with, where you typically just download the satellite data to your own computer and analyze the data by yourself. This is not something that is feasible anymore when we are talking about high resolution crop monitoring. So we need to rely on these cloud storage and processing facilities. Typically, these facilities offer the data already in an analysis-ready format. So that means that the necessary or a lot of necessary pre-processing steps and calibration steps have been taken care of for you. So the data is actually ready for use. And they offer that through various ways. This is just a grasp of all the available platforms out there where you can get these high resolution satellite data. I will go in more into detail in some of them at the end of the presentation, but just know that depending on the provider, well, not every data set is available on every data provider. So depending on your application, you would need to turn to other data providers and other processing facilities. Also, not all these facilities offer both storage and the processing capabilities. So some of the platforms listed here, they only offer the data and you still need to process it on your laptop. But others like Google Earth Engine, for instance, which is a very famous example, they also offer the processing capabilities. So you can just process the data on their premises and download the final result of your workflow. But more on that later. So we have the satellite data. We have a location where we can get the satellite data and also do our calculations. Another thing we need, or that has actually allowed the rise of parcel-based crop monitoring in recent years is the big advances in artificial intelligence. So by now we have many different machine learning, deep learning approaches, which actually help us to make sense of the terabytes of data that we get every day. And without those algorithms, it would be actually very hard to derive the information we need from that pile of data. So these three ingredients, the satellite data, the cloud storage, and the artificial intelligence, have really made it possible to further explore parcel-based crop monitoring. Obviously, when we talk about these, especially deep learning algorithms to make sense of all of our data, we also should immediately mention the need and the value of in situ reference data. So all these very fancy algorithms, they need to be trained to do a specific task, for instance, land cover classification, crop stress detection, etc. So that means that we also need, at the field scale, real data, real observations on all of these processes that we want to map based on the satellite data. So sometimes people tend to forget this aspect because they think, okay, we have the satellite data available, we're good to go. No, you always need to take this factor into account, that you need the proper training data for your area of interest and for your specific application to train your models. And this can be done either through in situ data campaigns or through installing some sensors in your field to measure some meteorological or soil moisture conditions, for instance. And in that sense, in terms of reference data, there are some promising and recent trends that I want to highlight. So for one, there is the GeoGLAM, so the Global Agricultural Monitoring Community, which is trying to standardize the definition of essential agricultural variables. So ensuring that we're all talking about this exact same thing when we're referring to, for instance, biomass or crop types. And at the same time, they are releasing some specific guidelines on how to collect these data in the field. So if you're interested in that, here are some links I provide for you to check out. On the other hand, we know that a lot of people are currently already collecting data at field scale, but this is mainly done on an individual effort basis. So what we're trying to do in the community right now is really to go and converge on these harmonized data sets. So where we try to bring together data sets from across the globe and make sure that they're all sharing the same metadata, that they're all sharing the same legend, etc. It's a huge effort, but especially if we want to go to global crop monitoring approaches at high resolution, this is really something we need. And there I provide just one example of the World Cereal Project, which is a project funded by the European Space Agency, focusing on cropland, crop type, and irrigation mapping across the globe. And there we actually did the effort of compiling this reference database, global reference database, on these topics. So also there, if you want to check it out, it's open database, and it's also you can also freely contribute to it. So please check it out if you're interested. And then the third trend I wanted to highlight is the involvement of crowdsourcing or citizen science approaches, where we actually provide apps for the broader public or for researchers to engage in reference data collection. So one example is a Crop Observe app, which allows you to very quickly register some activities which are ongoing on the field in terms of management. For instance, a harvest event, planting, fertilizer application, etc. It also allows you to report crop damage, etc. And then there's another type of apps which engage with the broader public, offering very high resolution images, which citizens can then start labeling. This is mainly done for land cover to acquire a lot of data on reference data on land cover. But it's just an example of how we are reaching out to the public to help us in gathering these data sets. Okay. Now, irrespective of the application that you're considering, and I will come back to the applications later, this is the general concept that we're using to do this parcel-based crop monitoring activities. So what we typically do is we start from a time series of optical data. In this, it can be, well, most famous example is the NDVI, the Normalized Difference Vegetation Index, or another one is the FAPAR. It's a measure of how green a certain pixel is in time. So this time series gives you a nice overview of the crop development in your parcel and what are the types of information you can derive from that. First of all, a phenology. With phenology, I mean the start, the peak, and the end of the growing season for a particular crop on your parcel. Crop type and the occurrence of agricultural practices. For a crop type, for instance, because each crop type typically has its own rhythm and its own timing in crop development. So based on these timing differences of key phenological stages, you can usually make pretty well the distinction between different crops. Also, obviously, in case of this blue curve, for instance, you see the main growing season here, and then there's the start of a peak here, end of September. So based on this, you can also conclude, for instance, that there's a cover crop being planted by the farmer after the main cropping season. Another thing you can derive based on the amplitude of this curve, you can start looking at crop stress during the growing season. And once you have the curve for an entire growing season, the area under the curve is actually very closely related to crop biomass and in a sense then also to yield. So those are the main information products that we can derive from satellite-based or optical-based remote sensing data. And for each of those, I will go a bit more in detail later on. So this is our main input into our model, this time series of optical data. In terms of models, we can either make use of empirical models, and there I mean it's purely a data-driven model. So it purely uses, on the one hand, the time series of optical data, and on the one hand, some reference data on what is actually happening in the field, and it tries to directly link those two in a machine learning model. On the other hand, you have these biophysical models, and there you try to actually simulate crop development based on our physical knowledge of how plants develop. And there, these remote sensing data are mainly combined with other data sources, for instance, climate data, digital elevation model, etc., or even other data derived from Earth observation. And yeah, the main differences between these two types of models is in the reference data needs. So the empirical models, like I said, purely based on these reference data. So there you have a high need for a lot and good quality reference data, whereas the biophysical model, there your reference data is mainly used to calibrate the model a little bit, but it should be more usable out of the box for an area which was previously not covered by your reference database. That's the main thing. Whenever you want to use an empirical model for your study or your application, always check whether it actually has been trained for the location and the conditions you're applying it to. And this is less of a concern in terms of a biophysical model. That's briefly the difference between the two. And so you combine these inputs into the model, you train your model or fine-tune the model, and then you produce these outputs. Output can be a classified image, for instance, of an entire area. This is an example of a crop type map here, or it can be a time series for an individual parcel. This is an example of biomass production across multiple years. As the time series of Sentinel-2 is such an important input into all of our parcel-based crop monitoring applications, we should be aware of this huge limitation that is imposed by clouds. So like I already mentioned, in some areas around the world, we scarcely have any observations of Sentinel-2 just because of the cloudy conditions. So we need some approaches to infer or derive information during the cloudy days. And this is an example of CropSAR. This is an application which has been developed at Vito, which uses actually a fusion of Sentinel-1 and Sentinel-2 data. Remember, Sentinel-1 data, you look through clouds. And this uses this information of the radar sensor to know what is going on in between the periods of time where you have available Sentinel-2 observations. So the green squares here are the available observations, the non-cloudy observations. And then the blue line is what CropSAR actually returns. So it returns an uninterrupted time series of your variable Sentinel-2 variable of interest. If you want to learn more, there's a link to this web service as well. Okay, before diving into the actual applications, quickly some words on the difference between a pixel-based approach and a parcel-based approach in crop monitoring. So very briefly, on the left-hand side, you typically see a pixel-based approach. So each pixel in the image is treated independently. And you use only the input or the data of one pixel to generate the output of that same pixel. The advantage is that these sort of applications are easily trained, easily scalable, require a bit less training data compared to the more advanced approaches on the right. But the large disadvantage is that, is exactly the fact that each pixel is treated independently. So this pixel is not aware of what is happening around around it, so not aware of the context around it, and that might lead to some clear artifacts, which we term salt and pepper. So this is typically this image right here, the left one, is typically a raw output of a pixel-based classification. In this case, a land cover classification. So you see each pixel has been classified independently of the others, and you get a lot of noise in the result. There are, however, some techniques to then smoothen out this noise and to get a more decent looking output. This is, for instance, the example of a majority filter here, where you consider the nearby environment of a pixel. You determine the majority, through majority vote, you determine the most abundant output, and you assign it to the center pixel. So that's the pixel-based approaches. Highly interesting if you're actually interested in what is going on inside your parcel. So if you're interested in the variability within your field, then obviously you should have a look into pixel-based approaches. Parcel-based approaches, then the concept there is that you already start from a predefined parcel, and you first compute the average Earth observation signal within that parcel. So based on all the pixels that fall within that parcel, you extract one time series, and then you use that time series as input into your classification or downstream application. So you get one consistent output for each of your parcels. Obviously, this means that you get a much cleaner result in the end. Also means that you lose this within field variability, of course. But this also means that there's a high requirement here. So you need to have these parcel boundaries already predefined or extracted based on the imagery. And that is actually an extra source of uncertainty in your analysis, because if you are slightly off in determining these parcel boundaries, then the downstream products will also suffer from these artifacts, obviously. And then fully on the right, there are also some hybrid methods, which I will not go into detail here, but these are typically deep learning convolutional neural network approaches in which the image is processed in one go. So that means that the objects are detected and in this case, classified at once. Okay, so a bit more on these parcel boundaries for the parcel-based approach. So like I said, either you need to have these parcel boundaries already for your application, and they can be manually delineated. But yeah, if you have a large area to cover, that can be a very tedious job. For some countries, these databases of parcel boundaries, they are there and they can be used, so that's nice. But for many, there are not, and they have to be derived somehow from the Earth observation imagery. And that is what we typically mean with parcel delineation. So that's what I want to tackle a bit more in detail here. So parcel delineation, usually based on an image segmentation technique. And briefly speaking, these segmentation techniques, what they do is they group similar pixels in the imagery together to delineate individual objects. So most of these techniques actually come from natural image processing, and they usually work with only 3 inputs. So a natural image also has 3 components: the red, the green, and the blue pixel values. So these algorithms typically only use 3 inputs to derive these objects. If we want to apply these techniques, these segmentation techniques on remote sensing data, where we have potentially a lot of observations throughout the season, then we'll need to find a way to select the most interesting observations as input for our segmentation technique. And that is what I tried to illustrate in this figure in the center here. So for instance, if you know that in a certain region, these two crops are very predominantly present, then you need to find a way to make the distinction between these two types of crops. And based on their typical temporal profiles, you could say, okay, I select these three moments in time as input for my segmentation technique because I know at these three moments in time, the two crops are most dissimilar. So it will be more easy for the segmentation technique to make the distinction between a parcel of, in this case, winter wheat and a parcel of potato. So what we then do is we compile these three observations into one image stack. So this is an example right here where these three inputs are combined into one image, and this is the image that is then fed to the segmentation algorithm. And here on the right side, I just show an example of this Felsenschwab method, segmentation method, which actually works pretty well for parcel detection based on optical data. So if you want to try that yourself, I would recommend this method. Obviously, this works pretty well if you have large homogeneous parcels, such as in large parts of Europe. But if you go to, again, smallholder farmer contexts in tropical Africa, for instance, there it is much more challenging to do this parcel delineation only based on three inputs. So that is where the more advanced approaches come in. So again, this is more deep learning approaches, convolutional neural networks, which instead of only using three input images as we saw previously, they typically can use almost the full time series that you provide, and they are able to learn themselves where the key differences in different crop types are. Again, I will not go into too much technical detail on these methods, but I provided some useful links for people who want to know more about this. So the first link is an example notebook where we actually demonstrate this, and you can just apply it yourself. And one other thing is a blog post from Synergize, a company who's also making quite good advancements on parcel delineation based on Sentinel-2 imagery across the world. So this is really a hot topic currently, I would say, in parcel-based crop monitoring. This parcels delineation. There's a lot of progress being made just using open data. And then, yeah, we talked about pixel versus parcel-based approaches. The right approach will obviously depend on your exact application. So again, parcel-based approaches where you just take the average of signal of the parcel and work with that. Typically commonly used when you want to detect crop phenology or crop management activities, where you actually want to summarize all the variability of your field into one signal and work with that. Whereas pixel-based approaches, they are more commonly used in classification tasks, for instance, crop type mapping. We normally use pixel-based approaches, but in case you have these parcel boundaries available for your area of interest, you can always use these parcel boundaries to clean the result of a pixel-based approach later on with a majority voting approach. So this is a bit the two approaches, and yeah, again, depending on the application, you will choose one or the other. Okay, so now maybe more the interesting part. So this was all a very lengthy introduction and to introduce some basic principles. But now onto the applications themselves. So the first one I want to cover is land cover and crop type mapping, typically done at high resolution or parcel scale. Um, Over here, we usually use supervised classification methods. So that means highly dependent on in situ reference data. So known fields where you know the crop type and when that crop type was actually present on the field. So those are the three main attributes that you need: location, timing, and the crop type label itself. Um, so what you typically do, you start from your reference data. You split that into a training part to train your model and a validation part set aside for later accuracy assessment. And for those locations where you have reference data, you typically start collecting your inputs. So you collect your Sentinel-2 time series for those locations, your Sentinel-1 time series. You pre-process each of the two data types, and I will come back to that later. You combine it potentially with some ancillary data. For instance, typically in crop type mapping, we use some meteorological data as well, or the digital elevation model, so elevation or slope, typically used. You make sure that all these inputs are nicely co-registered. You compute your classification features and select the most relevant ones. I will also come back to that one later. And you combine these reference labels with your computed features from the satellite data in your classification model. You train your model, and then once you have your model trained, you can just apply it to an entire area to get your classified image, right? So that's the general high-level overview of any classification approach using satellite data. As promised, some more details on the pre-processing. So although I mentioned that most data providers deliver analysis-ready data, that doesn't mean that you do not need to make some additional pre-processing corrections. Typically, the clouds in that time series that you get from the data provider, they are still there. So this blue line here represents the data as you get it from the data provider. And the red line is the final result after the pre-processing. So typically what you need to do is get rid of these dips here that represent clouds. Not going to in detail on that, but you can use the scene classification layer provided by the data provider as input for that. Then you do temporal compositing. We'll be showing that in the next slide, and linear interpolation. In case of SAR data, you need to filter out major precipitation events from your data because we know that during intensive precipitation, the signal of the SAR sensor gets a bit skewed. And then there are some other typical steps you need to take care of before you can actually use the data. There are actually many online tutorials on how to do these steps for both data products. Something about this temporal compositing, which is done after you remove the clouds from your time series. So this is typically how your time series will look like after you remove the clouds. And there you see that, okay, for some periods in time, you have a lot of observations in a very short time. For some periods, you have absolutely no observations and so on. And this is not what you want because what you want is to have a harmonized time series in the temporal domain, so that each time you use it as an input for classification task, for instance, the model can actually expect one observation at each time interval. So if the model, and in addition, needs to take into account these highly scattered temporal profiles, you will make the model's life a bit more difficult. So what we actually do typically is we take a fixed time window for instance, 10 days or 1 month. And for each time window, we compute the median observation within that window. So for each space between these two lines, we summarize all the data points available to just one median observation. And then the result of this temporal compositing is shown here on the right. So you have a more regular time series available in the end. Obviously, where the original time series didn't have any observations, you will create a data gap. And that is why in the previous slides, we mentioned that you need additionally interpolation to get rid of these data gaps. Okay, again to our scheme. So we have pre-processed our data after making sure that they have the same resolution and extent, etc. We need to compute some features, because obviously if you start from these lengthy time series of data, for Sentinel-2, you typically have quite a lot of bands or at your disposal. For most of the algorithms that are used for downstream applications, this is simply too much information to handle. There are some deep learning algorithms which actually can make sense of this data and try to identify the most crucial observations or information themselves. But for most traditional machine learning approaches, you need to summarize this this wealth of information in some way or another. So what you typically do is from the original time series, you compute some vegetation indices, some indicators which actually are related to the vegetation that you're investigating. And then once you have these time series of vegetation indices, you summarize that information, for instance, by taking the median over a larger time period, minimum, maximum, the variation across time, etc. You can also look at specific phenological indicators. For instance, based on these time series, you detect the start and the peak and the end of the growing season, and you use that as input for your classification algorithm. So this is just to say that you need to think about how to summarize in a meaningful way this wealth of information, also again, depending on your exact application. And this is what I mentioned here. So this selection of relevant features, either you do that based on your knowledge of what you're studying, or you can do this based on a separability analysis. And there, I mean, you compute a bunch of these potential classification features, and then you check, for instance, in a crop type mapping approach, which features are most relevant to make the distinction between the crop types of your interest. And then based on that analysis, you retain a few features that you feed to your machine learning algorithms. Talking about the machine learning algorithms for classification tasks, again, won't cover this in too much detail, just mentioning that up till now, most commonly used approaches, random forests, for instance, it has shown quite good performance, also with low amounts of training data, can be easily trained and applied, so it's not computationally intensive. So this was actually up till now the most commonly used algorithm, and it is gently being replaced by more advanced approaches. And there I want to mention this gradient boosting approach, for instance, which has been shown. It's also very easy to train, and and implement in your workflows, but it has been shown to outperform these traditional machine learning approaches. And an additional advantage is that it doesn't need any hyperparameter tuning, which in the case of random forest might be needed to get really top-notch accuracy. Other than that, you have these more advanced deep learning approaches. Recurrent neural networks is worth mentioning because they are designed to process time series. So that's what we're doing here, right? So processing time series into products. So these are well known to do that, but and I want to stress that for these approaches requires a lot of training data. So for instance, in my own work on crop type mapping in Europe, where we have quite a lot of training data, we typically use these approaches. But in other regions around the world, we have to revert back to either random forest or CloudBoost due to lack of data. And then if you want to know more about transformers, there's a link here for more information as well. So in a nutshell, transformers are based on these natural language processing models, which are now emerging. Think about ChatGPT. So they are also used in the remote sensing context and actually have proven to be very successful and even more successful than any other previously used approach. So that is something that is being explored a lot these days. Just 2 examples of products ready to be used by all of you, actually. ESA World Cover so produces land cover information at 10-meter resolution. It's based on this gradient boosting classifier based on Sentinel-1 and 2. So we have global maps available now for the years 2020 and 2021, freely available. And this, for your information, will be expanded in the future. So this product will get a yearly update and also some additional change detection analysis. So if you're interested in having high resolution land cover information for your project, then I highly recommend you to check this out. Likewise, there's World Serial. World Serial focuses more on crop type and irrigation mapping, also at 10-meter resolution. It's in the sense quite similar to World Cover because it uses more or less the same inputs. Also at 10-meter resolution. We have just finalized the first phase of this project, and the global maps for 2021 for wheat and maize have been produced. But we are now entering the second phase of this project, and there we want to make the system available for anyone. So the idea is that you'll have a system that you can run yourself and generate your own crop type maps for your area of interest and also other crop types aside from wheat and maize. So again, if you're interested in crop type mapping for your area of interest, just keep an eye on this project as well. I noticed I will have to speed up a bit, so we'll go through the other applications as well. Crop phenology, so detecting the start, end, and the peak of the growing seasons, also something we typically do at parcel level. So there, that's typically done at it's typically done by detecting these peaks in the time series and the associated local minima with these peaks, and then based on some threshold analysis, it's determined whether this is actually a valid growing season or if it's too low or too short to be a real growing season. So that's typically how these crop phenology parameters are determined based on this time series. If you want to learn more, there's this link to this paper here, which nicely illustrates this. Just mentioning that if you want to do crop phenology detection, you really need to make sure that you start from a very clean time series. So sometimes additional smoothing is done before growing season detection to make sure that you don't actually confuse with some remaining cloud artifacts in the time series. This slide here is just to mention that also crop phenology detection based on Sentinel-1 can be done, and depending on the crop type, it's actually resulting in very similar outputs as based on Sentinel-2. Just for your information. Also here a link to the paper if you want to learn more. Another application, crop stress. So typically for crop stress detection, we can use spectral indices. Many different indices have been established to cover different aspects of crop stress. So you have the drought stress indicators typically, but also specific indices have been created for chlorophyll content detection, nitrogen content detection, etc. The thing about this is, okay, if you produce a map of a spectral index, that isn't necessarily that informative. In order to interpret this spectral index, you need some sort of a baseline, because I don't know here in this field, this value, is that normal or is something really going wrong here? So what we typically do there is the concept of growth anomalies or crop growth anomalies. So you make comparisons, right? Either in space or time. So this is an example where you compare the crop development in one field with the regional average of similar crops in the neighborhood. And that is a way to know, okay, this field, is that really lagging behind the other similar fields in my neighborhood? Is my production actually going to be more or less compared to the average? So that's a way to make these crop stress analyses. Another way is, instead of making comparisons between different fields, is looking within an individual field. So this within field variability analysis, what you typically do there is you compute the average crop health of your field in a certain moment of time, and then you compare each individual pixel with that average. And so what you get as an output is the deviation of the average behavior of your field, and that allows farmers actually to detect less well-performing zones in their fields. And that's also a crucial input for this precision agriculture I was talking about. So in this case, the farmer, for instance, knows, okay, there's something wrong here. I need to provide more fertilizer or more irrigation in that zone of the field. I will skip this. Just for you to know, there are more and new sensors coming up that will allow to determine crop stress at more detail. Typically, a hyperspectral sensor, as opposed to Sentinel-2, measures measures radiation in much more detail, so you get much more information in one observation. And typically that allows you to determine in more detail things like crop water stress and specific nutrients at field scale. So this sensor is coming up in the future will be at 30-meter resolution, but it will also greatly improve our ability to detect specific problems in fields. Something I haven't really talked about yet is the use of thermal remote sensing data. I'm not going to go in too much detail, but just know that these thermal sensors, they just measure the temperature of your crop, and the temperature of your crop is highly correlated with the drought stress that or the transpiration rate, and hence the drought stress that that crop is experiencing. So there's a link here to more information on that, on how that works. But just know that by measuring the temperature of the crop, we can determine drought stress in pretty high detail, and also before you actually notice that something is going wrong on the field with the naked eye, or based on the Sentinel-2 data. This is just an example of such an indicator, which uses the temperature difference between the crop and the air temperature as an indicator for drought stress. Sorry, I don't have the time to really go in detail here. But if you're interested, check out the links in the presentation. Something to realize here is that this thermal data I was talking about is currently not available at high resolution. So it's currently only at 1 kilometer, 500-meter resolution available, so not at field scale. But there are some approaches out there which actually artificially improve the resolution of these products so that they become useful at the field scale. This is called thermal sharpening. And again, I have to apologize, but I don't have too much time to go in detail here. I want to highlight this SenET project, for instance, which is freely, the source code is freely available on GitHub. And this is using Sentinel-3 thermal data at 1 kilometer resolution, combined with Sentinel-2 data to derive this high resolution land surface or crop temperature at 20 meters. So if you're interested in crop drought stress assessments at field scale, this is one very interesting approach. Also here, do not despair. There are new sensors coming in. So one example is the LSTM mission by ESA, which will be providing higher resolution thermal data, also at a high revisit frequency. And there are actually others being launched in the next 5 years. So if we want to combine all this information, in the end, we will end up with high resolution thermal data almost every day. And this is actually very interesting for early crop water stress detection. So very interesting times ahead in that respect. Briefly on crop biomass and yields. So also there are two main approaches. We have these typical crop growth simulation models, which based on climate, based on soil, based on crop parameters, they model in high detail the crop development and biomass production and eventual yield. One example is this aquacrop model, which works normally without the use of remote sensing inputs. But these models, they typically get boosted, let's say, by using remote sensing inputs in a data assimilation approach. What you typically do there is you tune the simulations done by the model based on the observations from the satellite data. So that is one way to indirectly combine satellite data with a crop growth simulation model to derive biomass and yield estimates. Another way is to directly use the Sentinel-2 data as input for your model, and then we typically arrived at the light use efficiency models, which combine Sentinel-2 observations with temperature and radiation from meteorological data to estimate, first of all, this gross primary production, so the amount of carbon that is fixed through photosynthesis on a daily basis. This carbon quantity can then be transferred or translated to dry matter production. So what you get from these models is a time series of dry matter production. If you then know the start and the end of your growing season, you can compute the total biomass production over your growing season and then translate that into crop yield, actually. So that is a very popular way, let's say, of using remote sensing data to assess biomass and yield production at the field scale. And for the interested people in the room, this is just one of these tools available through Google Earth Engine that exactly does that. So if you're interested in there, please check out this Gimme crop yield tool. Another approach for crop yield is then to use empirical models. So the previous models, again, they use our understanding of how crops develop. These ones, they purely combine the remote sensing data input with a lot of data on measured yield data on individual fields, so directly in a machine learning approach, to estimate these crop yields. There, obviously, this quantity and quality of yield data at the parcel level is really crucial and determining how accurate your model will be. And in practice, this is often the limiting factor here, and that is also why these approaches are typically not that developed yet, because we simply lack the high quality yield data to train these models. In that respect, there is a growing trend to team up with the farmers here, because there's a potential win-win situation here. On the one hand, we lack the field level data to train our models. And on the other hand, the farmers, they might have this data, but they want to know upfront how much yield they can expect in their field. And so they can steer their crop management in order to boost productivity, right? So there's a potential win-win, and that is what is typically done in some data platforms that are out there. Two examples are Watch It Grow and IRIWatch. So there the idea is really to offer some services based on remote sensing data at parcel level to the farmer. For instance, these intra-field variability maps, as you see here displayed, this is automatically generated for the farmer based on the latest satellite observations, and he has access to those observations through this platform. And in return, the farmer can declare some observations. For instance, when he harvested, which crop type he planted, what was his final yield, when did he apply irrigation, when did he apply fertilizers, etc. And all this information can then help us as service providers to fine-tune our models and to boost the performance of our models so that they become more useful for the farmer. So this is, I would say, a big trend and an important one if we want to continue upgrading the performance of our parcel-based models. Okay, I realize this was a lot of information on what we can do using satellite data. So how do you actually get started with all these applications? Like I mentioned, there are a lot of platforms out there currently which offer data and processing capabilities. There are three I want to highlight. First of all, if you're just interested in looking at Sentinel-2 data or any data set from the Copernicus data ecosystem, so European data space, this Sentinel Hub EO browser is a nice platform. You can just go to and visually browse through the data that is available there, and download individual scenes. Obviously, when you want to do your processing or you want to build downstream applications, just looking and downloading the data is not sufficient. So there you really need to go to a cloud computing facility. First one I want to highlight here is Google Earth Engine. Nice thing about Google Earth Engine, there's a lot of Earth observation data sets integrated in there. And like I said, it also has quite nice processing capabilities, so you can run your analysis directly on the cloud and download just the result. Up till recently, you needed to know quite a bit of JavaScript, the programming language, to get started with Google Earth Engine and write your own scripts. By now, there is Python integration foreseen through a Python API, so you can use Python code to access and process data on Google Earth Engine. And a nice way to do that is using Google Colab. That's another more recent application launched by Google, where you can just it's basically a very nice environment to create your own processing scripts, your notebooks, as we call them in when working with Python. And it's also nicely connected to your Google Drive. So you can, for instance, upload some reference data sets to your Google Drive. You can access them through Google Colab and then also link that with the remote sensing data in Google Earth Engine to build your processing pipelines. And there are some nice examples, tutorials out there on how to get started with Google Colab and Google Earth Engine. Another platform I want to very much highlight is the Copernicus data space ecosystem. This is very new, just launched earlier this year. And it's basically the European alternative to Google. So it combines a very rich data catalog with the processing capabilities. So any user can just create an account on this facility, and you automatically get some free processing credits on a monthly basis, and every month your processing credits are replenished. So the idea is that just for developing your applications and running some demos, you can just freely make use of the platform. And as soon as you want to run an operational service, you will need to purchase some additional processing credits, as will actually be the case for Google Earth Engine as well, probably in the future. An additional added value of this Copernicus CDSE is that it's nicely integrated with OpenEO. I won't go into too much detail here, but OpenEO is just a way to process data irrespective of on which data platform the data is hosted. And OpenEO also tries to standardize the processing of Earth observation data very much. So they offer a lot of default processes which a user can just use for basic operations such as cloud masking, compositing, interpolation, but also making sure that all the data sets you want to combine in your analysis, that they are nicely aligned and covering exactly the same area, etc. So there, OpenAO is really a nice system because it provides you with a lot of building blocks pre-configured that you can just use. If you're interested there are some more advanced examples of how you can use OpenAO for agricultural monitoring, and I would encourage you to check these out. So from this CDSE platform, you can get access to both the data and the functionalities you need to get started with your application. Another advantage of this ecosystem is that it already provides pre-configured services for you. So for instance, computation of NDVI of these variability maps is already included there. You can just use the service as is for your parcels or your area of interest. And this algorithm plaza, as we call it, is continuously expanded with even more enhanced capabilities. So for instance, there are already some services available developed by Vito. Most of them I already mentioned in this presentation. So CropSAR, biomass estimation, crop calendar, so phenology, crop type classification. These are all services which will be integrated in this CDSE platform and which can be used by anyone for their own area of interest. So just to quickly wrap up some takeaway messages, parcel-based crop monitoring using satellite data, I think, is crucial if we want to ensure global food security and if we want to allow our farmers to boost their crop productivity. The recent advances in both the availability of free satellite data, cloud storage, cloud processing facilities, and artificial intelligence have enabled a lot of applications in this domain, and our possibilities are still expanding as we add more sensors to it. It's also becoming more and more easy for anyone to make use of the services that are being developed through these data providers such as Google and CDSE, where you can just get access to already prepared services for you. So these services are made more readily available to the broader audience. And as a last point, I really want to stress again that we need this high quality parcel-based reference data for any downstream parcel-based application. So if you have some data on parcels which you could share in these harmonized public reference databases, do consider to contribute to those. We're trying to get more data also through these crowdsourcing citizen science applications, but this is currently, in my opinion, the main bottleneck of parcel-based crop monitoring today. We have all the satellite data, or almost all satellite data and processing facilities we need. We just lack this reference or ground data. So whenever you plan a project in this domain, make sure to also include a component on collecting some data on the field. And that's it, what I wanted to tell you or share with you in this webinar. I realize it was a lot of information, so I have included a lot of links in the presentation as well for you to check out later on. I also want to make you aware very quickly that there is an upcoming face-to-face course in the EU Africa context to be organized January 22 to 26 in Senegal, exactly on this topic of parcel-based crop monitoring. And there we will go much more into detail into practical examples on how to get started. So thanks a lot. And if you have any questions, feel free to reach out to me. or just put them in the chat, of course, or the Q&A. Thanks. Yeah, if you have a very pressing reaction or you want to respond, yeah, exactly. You can just raise your hand without a problem, and I will give the floor to you. For instance, Jain, please interact with us.
Hello.
Hi.
Yeah. Hello, sir. Am I audible?
Yeah. Yes, you are.
So, I want to ask that you have mentioned that we can get parcel boundaries, right?
Yeah, that's one of the applications I mentioned.
So, how can we get these parcel boundaries from where, or is there any data available for parcel boundaries or something like that?
Yeah, so parcel boundary data availability highly depends on the country or region you're interested in. So for some countries, these databases are there and they're gathered through the government or some organizations. But if not available, you can either, yeah, like I said, manually delineate the parcels, which is a tedious job, or use Sentinel-2 data to extract these boundaries yourself from the satellite imagery directly. And in that respect, I mentioned these applications. Sorry, I need to scroll back a lot. Yeah, so this one, for instance, so where you use actually NDVI imagery as inputs in
Okay.
a trained model to get these parcel boundaries in the end. And here are some, yeah, I think it's a very active field currently. There's a lot of development ongoing. So here's a link of one company who's making a lot of advancements on that. But basically, there are more and more off-the-shelf models being produced that can do this type of work. Most of these models will probably not be free anytime soon, but they will become available as a service. I hope that
Okay.
answers your question.
Yeah. So,
Thanks.
sir, one more question I have.
Yeah.
Actually, we are monitoring the crops in over Indian region. So there is actually the Sentinel pass gap. Every alternate pass data will be is available here. Like the original pass is of 12 days repetition cycle, but every alternate pass data is not released over some region here. So how to fill this gap to monitor the phenology stage and other stages of any crop? Is there anything we can use?
Yeah. So I have been mentioning CropSAR, for instance. That's already a rather advanced approach, I would say. It combines Sentinel-2 and Sentinel-1 in one approach, in one model to get this uninterrupted time series of Sentinel-2.
Okay. Uh, but during the Kharif season, when there is a cloud cover,
Mhm.
the Sentinel-2 will not perfectly work at that time. So during those days, is there anything?
Yeah, so that's exactly the concept I've
Okay.
been trying to explain here. So the green squares here are the only points in time where we have actually an observation. So as you notice, there's a very long gap here, for instance, at the start of the growing season, where we simply don't have any observation. And there we use the Sentinel-1 radar data to fill in this gap. And actually, yeah, like I said, to fill the gap. So that's this CropSAR service is also available as a web service in our EO Plaza platform. So you can check it out there.
Okay. Sure. Thank you, sir.
Thanks for your questions.
Yeah. Thank you.
In the meantime, let me look at the Q&A a bit. I will start. Let me see some questions. Can the identification of cropland development at the administration? I'm not sure, Khaled, what you mean with cropland development, but if you just mean cropland expansion, or you want to know where what the cropped areas are in your watershed or administrative level, this can for sure be done. So I mentioned the World Cover and World Cereal project, for instance, where we are mapping cropland at 10-meter resolution at the global scale, and this can be repeated yearly to also do to check the changes at administrative level, for instance. So that is not a problem, can be achieved. And these classification approaches, they are pretty accurate nowadays. So depending on, of course, on the region you're in and the availability of reference data, again, for your region, the differences in accuracy can be quite big. In regions where we have enough of data, we typically get accuracies of more than 90% for both land cover and crop type detection. In other regions, like smallholder farming systems where we don't have any reference data, these 90% accuracies, they can obviously not be reached. So that's a bit of the trade-off there. Without in situ measurements, again, very difficult. What we do at the global scale to come up with a global product is we look at, if we have, for instance, in a certain region, no data at all, we use observations from similar regions in other places around the world. But again, it's very hard to get real accurate estimations or results without any in situ measurements. Which polarization is more suitable for radar crop monitoring? There really depends, Christina, on the application and the crop type you're looking at. So typically Sentinel-1 is VH and VV polarization available. In most applications, we just use the both polarization modes as input to our models. For instance, for cereals is known, but I actually forgot. Cereals is known to be very sensitive, either in one or the other. Sorry, I don't know exactly which one anymore. But for some crop types, it's more relevant to look into a specific polarization. But that's need to be checked for each application separately. So yeah, in areas of heterogeneous agricultural types, again, I'm referring to these smallholder farming systems. You need to realize that you're working with 10-meter resolution pixels. So if your fields are much, much smaller than these 10-meter, then yeah, there's obviously not that much you can do. You can make a bit of an abstraction there and try to map at a regional scale, more or less, the abundance of a crop type, for instance. But going to individual parcels in such a case is indeed very tricky. So there, again, we need to look into commercial data, for instance, the planet data, to cover that. And yeah, the links and the PowerPoint will be shared with all of you. Gadissa, with regards to your question on using low resolution satellite imagery for research work, that's a very broad question. Again, depends on the application. We have had in this series some courses on low resolution satellite data for various applications. Obviously, for parcel-based monitoring, not that much, but for ecosystem monitoring, for drought assessment at large spatial scales or at regional scale, it's definitely worth looking into low resolution imagery. Obviously, that will greatly reduce the computational burdens of your processing algorithms. So if you can solve your question using low resolution satellite imagery, then don't hesitate to actually use it. Yeah, like I said, for drought monitoring, we typically use 1 kilometer data to do this at a continental scale. So again, really depending on your question. Zainab, I'm afraid you will need to be a bit more specific on accuracy. Accuracy of what type of results? That's a very broad question. Um, so if you're still here, feel free to raise your hand so I can unmute. Then again, using Sentinel-2 to fill gaps in Sentinel-1, that's actually a very interesting question. I haven't thought about that because usually, yeah, we have the case that Sentinel-2 is lacking and we do have Sentinel-1. Indeed, now that one of the two Sentinel-1 sensors is out, we temporarily have a Sentinel-1 data issue. I think in most areas around the world, you simply won't have enough Sentinel-2 data to fill the gaps of Sentinel-1. That would be my first guess. But yeah, if for your region, you have the data available, you can definitely do so, I would say. It's just indeed of a matter of training a reverse model of CropSAR. So again, on this polarization, we simply use both polarization channels. And then a question on the reproducibility across regions. Is there a way that location details? Isa, I'm not sure whether I completely get your question, so I don't know whether you're still here. Can you maybe clarify that a bit for us?
Hi, good
Hi, Isa. Yeah, we can hear you.
Okay. Um, my question is regarding the reproducibility across regions. So let's say we build a model for somewhere in India. Can we pick this model and apply it somewhere in Nigeria?
And you're referring to what type of model?
So let's say for um, the land cover classification model, for example, which
Mhm.
has been built on features specific to places in a specific country, let's say India, for example, and it takes into consideration the geography of that region. And
Yeah, good question. Yeah, this transferability of models, that's a very important issue. So you always need to be aware of the type of model you're using. If it's purely an empirical model, so purely data-driven, it is always limited in terms of the extent to which you can apply it, or you need to make sure that you only apply it to conditions for which it was actually trained, right? So if India is very similar in terms of crop conditions and also crop types with your region of interest, then you should be able to apply that model for your area as well. If not, then you should definitely consider to take that model and maybe fine-tune it a bit using reference data for your area of interest specifically. So that is typically how you make sure that the model is fit for purpose for your area of interest. Yeah, that is also what we try to accomplish in this global mapping approaches and projects. We try to gather data from as many different regions as we can to make sure that we cover all the conditions that can occur. And then we are sure we can reliably apply that model to any region in the world. But if not, there will always be a risk of that. So I hope that answers your question.
Yes, thank you.
Okay, let me check the time. We are already a few minutes late. And I don't see any other questions popping up in the chat or any other hands raised. So I think we can close this webinar right here. So thank you all for participation. As said, the slides and recording of this will be shared through the EU Africa website, so you can at your own pace review all the materials that we've covered in this presentation. I know it's been quite a lot, but I wanted to give you a broad overview of the possibilities and limitations we're currently facing in parcel-based crop monitoring. So I hope it was an interesting one for you. Maybe one last question, Jane?
Hello.
Yeah.
Yeah, sir. So I want to ask, can I share? I mean, how can I share my data to you, and like, how can I access some data from your side? Is it possible?
Yeah. So there's one. So the one project I mentioned. Sorry, I will. Is the World Cereal project, and that is typically on crop type and irrigation and crop and land cover. So there, if you go to the website, you will find a page on reference data for global crop mapping. And there we actually host a global reference database with data from containing data from, yeah, like you can see from all over the world. And you can freely explore these data collections and download the data that you wish to use for your applications. And you normally should also be able to contribute to this database. Currently, contribution is temporarily switched off because we are in between two phases of the project, but we will for sure reactivate this again. So you will again be able to contribute your own data to this growing database. And in that sense, we can, together work on improving our models.
Yeah. So, like in situ data, right?
Yeah, exactly. There's also some guidelines on how to collect and how to structure and etc. your data before uploading it. So
Yep. Sure. Thank you, sir.
thanks for the question.
Thanks.
Okay, well, if nothing else, then I wish everyone here a nice remainder of the day, and hope to see you again in a next EU Africa activity. thank you all for joining and have a good day.